Pascal, we are very happy to have you here, and we very much look forward to your presentation.
Thank you. It's an absolute honor to be able to do this. It is strange to think about just how connected around the world we are right now. We would not have been doing this 15 years ago, probably. So this is an absolute honor for me. So thank you for having me. So today I have perhaps what is a broader rather than more specific presentation, but I hope it will share some insights from my background. As was mentioned in the intro, I trained in both psychology and physics. And so I studied a lot of things like differential equation modeling while also learning about psychological constructs and what was being done in psychology. And these really came together for me when I learned about dynamical systems from a physics perspective, thought this was absolutely incredible, an incredible way of thinking, thought this had to be all over psychology given what I knew about psychological constructs, and found far less than I was pleased with at the time. So I've spent a few years trying to fix some of that. Just so you know, I have a two-screen setup. So if you see me looking up like this, by the way, I haven't become bored of my own presentation. I'm looking at the time, or I'm looking at your videos. I can see all of you, at least those of you with active videos, not all the participants, but the panelists. So off we go. This was a strange presentation for me to prepare, quite frankly. When I was invited, the invitation was focused on methods for causal inference from longitudinal data. And given my background and interest in longitudinal data, I very much define myself in terms of repeated intra-individual observations. While I've done plenty of longitudinal data, the idea of causal inference is a little further from my mind. And so when I got the invitation, I was a little bit like, I'm not sure that longitudinal data is enough to get us from data to causes. Do you really want me as a speaker? And I got a yes, so I agreed to do this. But I think some of this part of the invitation may have come due to a comparison of two models that I did. A comparison of discrete and continuous time models, which can be both thought of as longitudinal models for mediation. And I'm going to show you those very briefly today. But in thinking about this presentation, I took another step and started thinking about what have I learned from working with those two models? When you put those two models side by side, what do they teach us about longitudinal modeling in general, but also things that we may need to consider or likely will need to consider if we want to move from data to causes. And so that's what I want to share with you today. I will introduce two longitudinal mediation models. They may be familiar to many of you, but those are the briefer part of this. The larger part is then thinking with those two models about things like the nature of time, the relations between system components, and what we can get from longitudinal data when we start thinking about causation. So our first model begins very simply, and all of these I'm using structural equation modeling, diagramming here. I'm using that RAM notation from McDonald and McArdle. And one of our simplest models that we start with is an autoregressive model, a model where we take our observations at some time and we regress them onto a prior time. And these models are terribly common. They are the basis for quite a few of our other models. You can think about cross-like panel models in this realm. You can think about many of our models from time series analysis. I know that Boulder and Laurenceau have talked about using these in multi-level modeling frameworks for modeling intensive intra-individual data. And there are many, many variations of this. We can start to think about multiple variables. We can think about the addition of random intercepts or means. We can think about multiple lags. Often we, in psychology, seem to focus on just lag one autoregressive models, but we could think about multiple lags. But this is the very basis of our initial thinking in many ways. That we could take today and we could understand something about today from yesterday. And so we draw a path there, a regression. If you want to think about it in SEM causal kinds of language, we can say yesterday caused today, and then there's some additional unaccounted for disturbances. But what's very interesting when you look at this model is that it seems to convey more and more, perhaps we interpret more on it than it really has. We forget something very basic from learning structural equation modeling. And that is that when we are fitting a structural equation model to our data, the best that we could say at the end of the day is that this model is consistent with our data. And I say consistent with our data because there are other models that we haven't fit that could produce the same implied covariance matrix. And that's a little bit strange to think of an autoregressive model. We regress one onto the prior time. There's one correlation, one covariance. What more could there be? But in reality, when getting from yesterday to today, we could start to think about there being many paths from one time to the next. That while we draw this very straight linear path in our SEM models, what was the person doing in between? Were they perhaps varying back and forth? Or were they perhaps showing some growth and decline during that time? Was there a lot of stochastic perturbations in between that causes a lot of variation? There are many ways to get to tomorrow from today. You will make many choices getting to tomorrow from today. But in our modeling, we often don't take that into account. But there are many paths that would be consistent with the same observed covariances. Now, the argument against this is often, well, I only have 2 time points. I don't know anything about the time points in between. Well, that's not entirely true. We can actually start to put a model in between here. And one of the amazing things is that different models that we would replace this path with would have different implications for the covariance matrix. And particularly when we start to think beyond 2 time points, when we start to think about 3 and 4 time points, we actually have more information than just the correlation between any adjacent observations. We also have information about how the variance is changing, how the means are changing, how things are correlated 2 days apart or 3 days apart. So how do you go about doing this? So the place to start in understanding how to do this is to think about latent change scores. And these are a common, and I've taken kind of the simplest version of latent change scores here. But we could start to think about your score tomorrow being equal to your score today plus some change. And in order to identify this, we usually say there's nothing else here. We say this is a variance of 0. So tomorrow is equal to today plus some change. I'm going to make a minor amendment to this. I like latent change scores, but I would rather change these to latent velocity scores. That's that physics part coming out for me. I would rather change this to velocity scores. And you can see that I made a dramatic difference here. I changed a value of 1 on the path, that value of 1 here on the path. I've changed that to dt, the change in time between my 2 time points. And then I've rechanged my latent variable from change to change with respect to time, the amount of change divided by the amount of time. And this is a velocity. You can think about this as being related to speed, but if you're only driving in one direction. And you know this formula well. If you've driven down the highway, you've tried to figure out where am I going to be in an hour, and you know where you are now, and you know how quickly you're driving. And if you multiply by an hour and add them together, you find out where you will be. So you're very familiar with this, even if you don't talk in velocities like I do. So that's a very small change, and it's a model that works well and does something absolutely remarkable. There are ties here to calculus. I know we don't necessarily, most of my classes don't want to talk calculus, light stuff for a presentation, but what we're doing here is really taking from one time to the next. We're assuming the velocity is constant, and we're solving for the area under the curve. In this particular case, area under the curve is very simple because we can take the amount of time and multiply it by your current velocity and get the area under the curve. And you know this well actually from the highway too, because you know that if you can drive at a consistent speed, if you can keep your speed constant, then you have no problem figuring out where you're going to be in an hour. Once we start to think about psychological constructs, the idea that from today to tomorrow, your velocity, your rate of change on anything I could measure about you, depression, anxiety, affect, stress, whatever it is, the idea that that would be constant, that your scores would just keep increasing linearly from today to tomorrow, seems a little strange. You probably have something more where you're varying back and forth, where you have positive gains and losses. Your affect might be going down during certain parts of the day and increasing during other parts of the day. Hopefully this is not one of those down parts of the day, this talk. But your velocity is inconsistent. If you were thinking about this in a car, the picture here would be depicting you driving away from home and then driving back towards home. A negative velocity moving away from home and then a positive velocity back towards home. And if I take the average velocity there, if I take one estimate for velocity and I estimate the average there and I use that to estimate the average under the curve, I get a very poor picture of what you've been doing during the day. What I get, if I'm thinking about this in terms of position, is that you essentially went nowhere. You left your home, you came back. I don't know anything about what happened in between. Time 1 and time 2 are two squares in our autoregressive model. I don't know what happened in between, but I essentially say on average, you didn't go anywhere. But you went a lot of places and you will go a lot of places today. So to say that your average velocity on stress or on affect is exactly the same because I don't see it between two time points, well, there's a complicated path in between. But we need to start estimating the area under that curve. In order to figure out how you're traveling, we need to know that area under the curve. To depict this, or to start to think about how we do this, I've never presented a child with this, but I feel like you could present it to a child or a 19th century mathematician by the name of Riemann. You could draw more rectangles. So we've gone from one rectangle to more rectangles. And I know at this point, it's great to say, okay, yes, in theory, great. If we add more and more rectangles, we get to what the solution is in the limit. That's just calculus. Great, we can do that. I don't really want to do calculus. So what does this look like for us who are more familiar with SEM? In SEM, it looks more like this. Now I've adopted a little bit of my own notation here. This is supposed to be kind of an ellipse. It's supposed to be where you fill in the infinite more circles that the infinite number of latent states that I've dropped out of this figure so that it would fit. But then we want to imagine that there are not only 3 latent circles here, but 100, 200, 1,000. There are many moments throughout the day. And each moment is related to the prior moment and some change. We ideally would run this dt down to something infinitesimally small. This is the exercise of calculus. And we are making some inherent assumptions here. We're making an assumption that the construct, whatever it is, continues to exist throughout the day. So if we're thinking about affect, that you have something like affect, that we could in theory query your affect at any point in the day, that it does in some ways exist. But I talked about making different paths. Right now, this is a very boring model. There's nothing defined in this latent variable. So what we need to start doing is saying, how do you change from one day to the next? And there are many ways we could start to think about it. We could theorize many different ways about how do you navigate your days. One common pair of things that we do with this model is we will say that from moment to moment, you have some stochastic perturbations. You have perturbations because, quite frankly, we are living as open systems. From the dynamical systems perspective, or you want to take the physics perspective, if you think back to physics, it's about very closed off experiments. You don't want the extraneous influences, those things that come from an open system. So you close the system so you can control all the pieces. Unfortunately, we can't do that with people. People are open systems, and we are constantly bombarded by things from our environment. And so we could start to imagine that there are stochastic perturbations. From moment to moment, there are stochastic perturbations, and at every moment of the day, this could be occurring. And the variance of these probably depends on time. For any given moment, maybe a stochastic perturbation is pretty small, but if you add up many of them, you add up all the perturbations of the last hour or two, it may add up to something bigger. So there may be some dependency here on time. But perturbations due to us being open systems, systems that are affected by things extraneous to us. We can't put people in a box. We could also start to imagine things like self-regulation. Psychology seems to love this idea that we might tend towards some kind of homeostatic or self-regulatory level. And we might posit that wherever you are right now, if this is perhaps your stress, if you are very stressed, perhaps the subsequent change will be such that you try to rein that in some. If you start to get really stressed, you go for a walk, you do some exercise, you breathe a little bit more, you hide that email and say, I'll get to that another day, whatever the coping mechanism is. But you get very stressed, and maybe that affects how you're then going to change in the next moment. What we've done here is we've specified one way to get from A to B, from today to tomorrow. And actually, when you specify a model like this, as opposed to other models, you put constraints on the implied covariance matrix. Particularly when we have 3 or 4 or 5 times or more times, you start to put constraints on how that covariance, what that implied covariance matrix should be. And remember the fundamental mechanics of SEM. We come up with that implied covariance matrix from our model and the parameter estimates, and it gets compared to our observed data. So that the fact that different models, different paths, even between 2 time points, or 3 or 4, it doesn't need to be intensive intra-individual data, allow us to map different ways of getting from today to tomorrow, to allow for velocities to change across time, means that we can actually start to look at different paths from getting from today to tomorrow. What I'm drawing here, I said there were 2 common things that are added, these stochastic perturbations that are, if you integrate over any amount of time, are independent and normally distributed, combined with this self-regulatory piece. Really, it's a relationship between the 0th and the first derivative, between level and velocity. That is the exact discrete model. And it is a model that has been, that we've seen many times because it's one of our first order stochastic differential equation models. In order to deal with those stochastic perturbations, they had to invent new calculus. And it was only in some ways recently, I think it dates back now 70 years. So that's recent in knowledge terms, that we figured out the calculus for this. Actually, it might be more 75-ish at this point. I have to double check my dates. I take this as a starting point because, again, it takes us away from just the today to yesterday autoregressive model to saying there is some path carved out, and this has put constraints on what that path can be. I'm going to, throughout my slides, I've used a method called integration of stochastic differential equations. I need more flexibility with this model than the exact discrete model allows for. And so I solve quite a few problems approximately. I take literally what you see in front of you and I put in the constraints, but I will do this with 1 or 2 or 300 latent variables between each time step. That's actually quite doable with today's computers. You need some tricks to pull it off, but it allows me to fit certain stochastic differential equations that I can't fit directly with the exact discrete model. But at the end of the day, those are asides. What we have right now is the idea that we could fit these direct paths, or we could we could put down some kind of model that specifies a more constrained path where how you travel from moment to moment is a combination of perturbations and self-regulation. So again, the mediation, thinking about this in terms of a mediation context is probably what got me here. So I have sprinkled throughout this some data sets. We don't need all the details of these data sets. I will circulate my slides at the end of the presentation. I know this was going to be recorded, so you can always go back if you really want to see the details. But the idea here is an idea from the literature where anxiety and depression affect social competence in grade school children, but that anxiety might actually be a precursor to depression. And so we have very much a mediation kind of setup here. And I want to contrast those two perspectives that we started with, this autoregressive and something much more continuous, where we specify your paths over time. And I'm going to use a variations of things that I think Ellen Hummaker has put this out, and I think I saw her earlier today on the participant list. I don't know if she's still here. What I'm doing here is I'm taking observations, our data at any given time, and I'm literally splitting it into two pieces. I've called it here time varying and time invariant. Some people in psychology will think about this as state and trait. And what I've done here in blue is I've allowed each person to have their own mean. There's a mean across observations. This is, again, why you might draw a parallel to trait. I say this would be most appropriately called probably a random mean rather than a random intercept, because it really is the mean value for each person. And then in the upper part, above the squares, I take care of that time varying part. So what I'm imagining for my psychological data is that there are, in this short interval, because I'm only dealing with 3rd, 4th, and 5th graders, so I'm only looking at people over 2 years, that they essentially have some kind of constant trait around which they vary. And I want to model that state variation. And what I have here is a cross-like panel model. And it may not be immediately obvious to see, but if we start to look at the paths carefully, we have the effect of anxiety affecting 3rd grade anxiety, affecting 4th, then to 5th. Same thing for depression. So our variables are labeled here, depression, and then social competence. So we have those autoregressive paths. And I mentioned with the autoregressive model, of course, we can have multiple variables. So we have a case here where we have anxiety affecting depression, and then depression affecting social competence, so that there's an indirect effect of anxiety on social competence, but that there's also a direct effect of anxiety on social competence. This is a model that has been proposed as one alternative to, this is now a 20-year-old idea, of course, but this is one alternative to using cross-sectional mediation. That we need to incorporate time in some way into our mediation models, because if we work only with cross-sectional data, Maxwell and Cole showed this, that we often derive the wrong inferences. If it really is a longitudinal process and we use cross-sectional data, often we gain the wrong inferences from that data. And so the cross-like panel model has been proposed as one model that might allow us to test that mediation-like hypothesis, moving us towards perhaps causality. We can take that same model that I did before, and I've replaced all the latent variables with dots. It's easier for me to draw than putting in a few hundred latent variables, but this is meant to be that stochastic differential equation where we have the stochastic pieces and that self-regulation, but that we're doing some integration. We're doing something like a Riemann sum or integration in between. And we can actually swap that right in for the red part on the cross-like panel model. It's a different model for the states, how you get from one point to the next. It's an alternative to this autoregressive model. And the specification of cross-lags is a little bit different, but we still have the necessary pieces where anxiety, the level of anxiety is going to affect how your depression changes. Your level of depression is going to affect how your social competence changes. So you have something like an indirect effect there. And then you have a direct effect, anxiety to social competence. So we have two models that I've been thinking about. And I know this is a lot. These are just horrid models to put on a slide. This is why I said it's all being recorded. You can go back and stare at these all day if you want afterwards. I'll give you my slides afterwards. But bigger point here. We have our first model that is essentially a cross-like panel model of random means. A second model, which is this exact discrete model of random means, a little bit of a different specification than the random intercept term that is sometimes specified in the exact discrete model. And when you fit these two data, you get equivalent model fit. What I mean by that, by equivalent model fit, I mean you get exactly the same chi-square, you get exactly the same degrees of freedom. You'll see I've added a few covariances, that's why the pictures got a little bit more complicated, but there is a way to specify these so they fit the data exactly the same. They are both consistent with the exact same data. And this is where I wanted to start my, it feels a little odd to be this far into a presentation and say I'm now starting my presentation, but this is where I wanted to leap from. I wanted to give you this idea that we could have something where we essentially make no specification of path, the autoregressive model, and something where we have this very detailed specification of how you get from A to B, and that they can produce the exact same fit to the same data. The exact same model implied covariance matrix. And so in thinking about this, I wanted to bring up those three considerations: nature of time, the relations between components, and how longitudinal data relates to causation. What have I learned from these three in terms of longitudinal, or from these two? What have I learned from these two in terms of longitudinal modeling? With the hope that what I'm going to share about longitudinal modeling might also inform your thinking about causation, from going from data to causes. So the nature of time. The first thing I want to highlight is that when you look at these two models, I've drawn the two models here, and you'll see there's the first model, that's that autoregressive. The second model is my exact discrete model variation. Really, it's an exact discrete, it's supposed to be exact discrete here, except that I've only put in one latent variable. And I've only put in one latent variable just to keep this as simple as possible, because you don't need more than one latent variable in between observations to realize something about longitudinal modeling. When we work with the cross-leg panel model, we say this is the direct effect. This is the direct effect of X to Y. When you look just briefly at the second model, and this is where you have to apply those tracing rules that you learned oh so long ago, might need to refresh on them. But if you had to say, what is the covariance? How do we define the covariance between X at time -1 and Y at time t? Well, you would have to trace all possible paths. But this puts a little bit of a conundrum in our minds. When we have two time points, we very readily say that this is our direct effect. This is our direct effect. I meant to get a little bit of a better color there to stand out. There we go. There's our direct effect. But as soon as there's the construct exists in between our two observations. So if we're measuring anxiety in grade 3 and grade 4, if anxiety existed for even one day in between, well, we now have a combination of indirect and sort of direct combined with autoregressive effects. And so we now have an odd way to think about this thing that we call the direct effect. It seems very plain. In the cross-leg panel model, this is the direct effect. But as soon as you start to conceptualize that your construct may exist between your observations, you start to realize that what we call direct effect in the cross-leg panel model is a combination of indirect effects, direct effects, and autoregressive parameters. Two models, both consistent with the same data, but our definitions change depending on how we treat time. And so whether you think in very discrete terms like the cross-leg panel model, or very continuous terms like mapping out this path of the exact discrete, or the cross-leg panel model for discrete modeling versus trying to do this continuous time modeling like the exact discrete model, our definitions, our understanding of the data, our inferences change depending on how we incorporate time into the model. And I know that some of this has turned into there's a whole literature about discrete versus continuous time. I am actually not here to sell you on one or the other, because I've run into some problems when thinking about psychological data. I know that there's a temptation to say, okay, which one is more appropriate? And I know that when we measure, our measurements are always in discrete time. I know the true nature of time is continuous, but the true nature of psychological constructs, which is the area I think a lot, I'm not sure. When I start to think about things like depression and anxiety measured every 6 months, if I start to think about what happened from January to July, and maybe this is a COVID study given the present, I'm doing something with depression and anxiety, the idea that you jump that there's kind of that straight line path like the autoregressive from July all the way back to January, and that there's no path in between. That doesn't make sense to me. What makes sense to me is that I probably should be treating this as something more continuous, more along what the exact discrete model can give me. And I would want to put in many, many latent variables and describe that path. But then when I start thinking about something like peer victimization, if I think about my grade schoolers again and peer victimization, and one of the times that peer victimization may happen a lot is just at recess every day, but it may not happen at other times in the same way or at all. Well, then we almost have a construct that only exists for a narrow period of each day. Whether you're being victimized may not exist in the same way in between or at all. And this reminds me of studies in ecology from the dynamical systems literature where they're thinking about populations of various animals. And they modeled that with discrete time because many of these animals have, one time of year that they have their births. And so you can pretty much measure just right afterwards and know where the population is. But it's much more discrete. The problem with psychological data is, once again, I think a lot about intensive intra-individual data. And so when I start thinking about things like ecological momentary assessments or diary data, places where we're getting many observations during the day, and I start to think about things like, okay, maybe my affect interacts with my child's affect. The reality is that there are very brief periods during the day, in blue, where we even really have an opportunity to have that interactive element. There are large swaths of the day in red. My kids are not here right now. My affect's not affecting theirs. Their affect's not affecting mine. And then there are times that we're both asleep. Hopefully both asleep. If you have kids, you know that that doesn't always happen, but hopefully we're both asleep, and that's in the gray periods. And the problem with sleeping, I've questioned, does my affect exist when I'm sleeping? I know that if you were to wake me up, you probably could measure my affect, but it would be a very different number because you woke me up in the middle of the night. And so what we have is not necessarily discrete or continuous. It's what in many cases might be something that most appropriately might be modeled with some combination of discrete and continuous, or at the very minimum, perhaps a continuous model where the parameters can't be constant over time, where we have to have changing values across time. So time is unlike any other dimension we sample. I know it's continuous, the sampling is always discrete, but there is some interaction between sampling rate, constructs, and how time is modeled. And these will change our inferences. Depending on how often you're sampling, how quickly your construct is changing, or whether it even exists at certain times, and then how you choose to model it. Whether with just an autoregressive or mapping out paths or having changing dynamics, changing parameters across time, this will change our inferences. And to me, this seems like a roadblock for causation kinds of inferences, because can we get to the right model or a close enough model? It seems like a hard problem. Although it might depend on things like our sampling rate. It might be a whole lot harder with intensive intra-individual data. But it makes me think that one of the things that we might do in stepping forward is to start thinking about time not as an index. I know that time often appears in our data sets, and sometimes it's like the participant number. It's an index. It's just marking things. But maybe we need to think about it more like a variable in terms of how we consider it, how it enters into the model, how it's affecting different parts of the model. That was my first thought when thinking about these two models, when you compare the cross-like panel model and the exact discrete model. Relations between system components, a completely different thought now. Now for something completely different. I have another study here. This is the peer victimization study. These authors do not, I don't know that these authors know that I did this. They published their covariance matrix, which is very convenient from an SEM perspective because I can do things. Part of the reason for doing this was entirely a proof of concept that you don't need super intensive data to run things like the exact discrete model. There's something about carving out a path from one time to the next that people think, oh, I need to have super intensive data and I don't have that. This was a proof of concept that that's not the case. But you can see I've laid out, they had a time 0, a time 4, a time 7, and you could see they had this mediation-like thinking where peer victimization affects emotion dysregulation, but both emotion dysregulation and peer victimization affect your internalizing symptoms. So what else can we do with this? Because when we look at this, I mean, when we look at the data layout, it does feel like we only have one question, or maybe three questions, but I'm going to focus in on one. Does peer victimization predict emotion dysregulation? And we have to stop for a moment and ask ourselves what we really mean by this. And I think there's something in our thinking that is very cross-sectional. There is something that being grounded, or because we start our statistics classes in cross-sectional data, our first thinking is, okay, well, peer victimization, we're gonna regress emotional dysregulation onto peer victimization. We're gonna find out whether peer victimization predicts emotion dysregulation. Boom, we're done. That's from stats 101, right? Either from our first stats class or second stats class, you keep on going onwards. I think that once we enter the realm of longitudinal data, we need to retrain our brains. We need to retrain away from that cross-sectional thinking. Because if I were to change this question for a longitudinal data set, I would ask something more like, what patterning across time of peer victimization? How does peer victimization have to vary so that it results in a change in emotional dysregulation? And once you start going down this path, it's a little bit of a thorny path. You get into the weeds very quickly, but you start realizing there are different aspects of peer victimization that could relate to changes in emotion dysregulation. It could be the level of peer victimization. People who are victimized more versus less. Maybe that is the key for tying to emotion dysregulation. Maybe it really is just as simple as that. But you only have to look very briefly into psychology to realize, when you think about things like abusive relationships and such, it isn't necessarily more or less that will relate to those psychological outcomes. Maybe it's something like a linear increase in peer victimization. Maybe you have a bully, but the amount of victimization has increased. There's been a change. And people are very sensitive to change, right? I mean, over and over in psychology, again, you kind of see, okay, we love change. We are programmed to see change. And so maybe it's the change in peer victimization. And here, I mean, in a linear sense, it's just some kind of increase that relates to emotion dysregulation. You also don't have to know very much looking into psychology to realize that sometimes we're not very good at small incremental changes, or at least we're not very good at detecting small incremental changes. And so maybe it's only nonlinear changes, something like acceleration, something where the bullying or the victimization increases faster and faster that we pick up on it. When is this going to matter? I'm imagining two situations here. Red line is the peer victimization increasing. And I'm imagining that we had a child that was on some trajectory before the victimization started. They were on some trajectory, but the victimization has changed that trajectory. And if we were to look at something like this, okay, great. The lines go together, more dysregulation with more victimization, it looks great. Until you start to consider that perhaps kids exist before they enter our studies. And perhaps this child was on a downwards trajectory. The right-hand figure here actually the right-hand figure poses a major problem for us. Because if we were to correlate the observed levels, or we were to look for a slope-slope relationship, these two don't look connected to each other. The child is definitely, the dysregulation part of the child is definitely turning in response to being victimized. But if we do it in terms of just observed scores, or if we look at slopes, the peer victimization is going up, but the dysregulation on average is flat. It's not obvious that these are connected. So the reason I'm bringing this up is because one of the major things that we need to also think about is, given our sampling rates, given the constructs and how quickly they are changing of interest, are we expecting changes that are in tandem or not? Do we expect something more like the left figure where one person in a partner changes and the other just dances right along in tandem? They are in perfect harmony in their dance. Or do we expect something more like this other figure, where one person starts to change and it promotes changes in the other, but it takes some time for those changes to be realized? I know that if you were to measure aspects perhaps of my marriage over a course of every 6 months, it might look more in tandem. This might not be an unreasonable approximation, but if you were to go daily, the daily changes I might make to promote certain benefits to my wife, those take time to realize. And that happens with a lot of interpersonal relations. And so even with the same constructs, the same people, you could have both in tandem or non in tandem depending on our sampling rate. And the reason I bring this up is completely because in those pictures, the in tandem, whether you analyze observed scores or straight line change scores or acceleration like curved scores, you will get the same answer over and over again. With the non-tandem dance, you will get different answers depending which derivative relations you look at. And so I started thinking about this peer victimization, and I started asking the question, is it the level of peer victimization or is it the change in peer victimization? And then what's amazing is you can compare these models because they imply different covariances across time. It's a different path between the two time points. Is it the level of peer victimization that relates to emotional dysregulation, or is it the different level of peer victimization in red here, or is it the change in peer victimization? And I'm doing this with very limited data, but it does produce a difference in models. It does produce a different implied covariance matrix. And so we can compare these different paths. And this is why I was saying when we have time 1 and time 2, it may seem like we can't compare, we don't have any data there, except that when we put those, something like the exact discrete model or a variation like this, where we say change is related to change, those carve out different expectations for the implied variances and covariances. So when it comes to relations between, when it comes to thinking about time, again, longitudinal models, another thing that I think, aside from the nature of time, we need to be thinking about for our sampling rate, for our rate of change in the constructs or people that we're studying, are they approximately in tandem? And if they're not in tandem, we need to start thinking about, is it a level? Is it a level to velocity? Is it a velocity? Is it a level to acceleration? What is the relationship here? Because just because two things are coupled, they might turn in response to each other, but that might not be evidenced in the observed scores. And that's also, I feel, going to be very difficult for when we think about causation. And well, I know I'm at 45 minutes. I'm going to be done within 5. I went longer than I thought. So I'm watching the time. One more thought. Again, something completely different. Longitudinal data and causation. And this is the one perhaps foray into actual causation kinds of thinking that I've had. It was an intervention-based study where you had, it was a preventive intervention for children with parents with a history of depression. The children reported things like secondary control coping and anxiety depression. And we essentially, they entered the intervention, and after a few months, you kind of see them stabilize. And I modeled that stable period with a 2-group SEM comparing a control group with the intervention group, with the active dose group. We have a randomized experiment. And whether you use model 1 or 2 from before, cross-like panel model or the discrete model, we put in the random intercepts or the random means for both. We see a mean difference. Doesn't matter which way you model it, you will see the mean difference in these data. So we have control over the independent variable. We have a randomized experiment. We have a mean difference regardless of how we model it. What more is there for longitudinal data to offer? Is there anything more? And this was a problem that I wrestled with for a little while. I was trying to think, what do we gain? Why should I say we need to collect more data? We do these intervention studies all the time. You know, we complete the intervention and we do a follow-up maybe at 6 months and 12 months, and then we stop. But why do we need to collect more data? And thinking from a dynamical systems perspective, one way of thinking about these data from a dynamical systems perspective is in terms of attractors. And this is a whole nother language, but one way you could imagine it is that there's some kind of topology as to how our constructs vary across time. And you can imagine a little ball rolling on this topology. And there may be some wells in this topology such that if you are a little ball rolling around, you might get stuck in one of these wells. And perhaps the point of an intervention is to push you over from one well to the next, to push you into a new set of dynamics. Maybe that is the goal of an intervention. Maybe it's not just moving one of these wells, but it's actually trying to get you up and over into a different, attractor. One of the things that when you start thinking about that is, what are the chances that these two wells have exactly the same topology? If you want to imagine them as bowls, I pull out two bowls randomly. You know, if I go to the store, I pull two bowls randomly. You know, what are the chances that they have exactly the same? And I guess that's not good at a store because they have hundreds of each bowl. But at least for a person, we kick them into a new bowl, a new area of this attractor. What are the chances that's exactly the same? And so when we started looking at these data, I fit that variation of the exact discrete model. And I'm going to go very quickly through these results, but basically these are all the boring results. And the key values here in terms of p-values do a comparison. These p-values are representing the difference between the two groups, whether the parameter is estimated as two parameters individually for each group or one parameter the same for both groups. And you find that there is a difference in the mean of anxiety. There is not a difference in the mean of social coping. You find exactly the same thing with the cross-like panel model or the exact discrete model. What's more fascinating, though, to me, aside from that mean difference, and I know that is our standard for intervention, mean difference, is what this data tells me or may tell me about what the intervention did. Because when I start to model the dynamics, those paths in between, what I see is, in terms of what might be thought about as anxiety self-regulation, there's no difference. In terms of social coping, there's no difference. In social coping self-regulation, there's no difference. In terms of how they're coupled one to the other, there's no difference. So I haven't changed the relationship between these two constructs. But what I do see is the stochastic perturbations, those external influences on anxiety and depression, are different for the two groups, and they are smaller for the intervention group. And moreover, the covariance between, which might relate to kind of a third variable that affects the stochastic perturbations on both social coping and anxiety, are different for the two groups. And so what we may have done is not change the interplay. This intervention may not have changed the interplay between anxiety and depression and social coping, and it may not have even reduced the mean of social coping or increased the mean of social coping. It may not have changed that mean, but it may have changed the evaluation, how people are perceiving perturbations that come from their external environment, particularly on anxiety and depression, as well as perturbations that affect both depression and social coping. So when I'm asking, you know, what more is there for longitudinal data to offer? My answer to this was, we often think about longitudinal data as in the pursuit of causes. We're trying to get longitudinal data so we can infer cause. But I think this opens up a realm of what do we even mean by causation? I think we often mean some kind of mean or score difference. The score increases or decreases. But what this starts to point out is that when we start thinking longitudinally, we could start to think about differences in variance and how different constructs carve that path across time, how two or more constructs covary, or even things like the effects of external perturbations, those stochastic perturbations from our external environment. And maybe those are the things that will give us greater insight to our interventions above and beyond that mean difference. And maybe my untested hypothesis is maybe that understanding those processes will be the difference between understanding an intervention that fades out over time versus one that has a more lasting effect. And so this is why even experimental data, even when we can infer cause, may benefit from longitudinal data. So very quickly, nature of time. Our inferences will change depending on our concept of time. And our data may not fall neatly into being modeled as continuous or discrete. We need to think about whether constructs change in tandem or not, because if they don't change in tandem, if we're sampling at a rate where they don't change in tandem, the relations that we specify will change our perceptions of the data. They will change our subsequent inferences. And causation is so much more than just a change in value. It's so much more than just that mean change or some kind of blip in response to it could produce changes in how we vary across time within constructs or between constructs. All of what I've said today ties to various things I've written, and that's what these are. Again, I will circulate the slides so that you can see all of that. Thank you very much.
Thank you very much, Pascal, for a brilliant talk. I almost lost track of time just listening to you, but we do have some time for discussion. So if you have any questions.
Yes. So I can see the chat here. Let me move this.
And since we're in the discussion, you can also just raise your hand, or the people on the panel can also just unmute themselves.
So you made, there was a comment from that mathematical ability, for instance, might inherently be discrete because we can only measure it at certain times. How would I model such a construct in a continuous time framework? I think the challenge that I run into over and over with the continuous time framework is thinking through what is the path from one time to the next. And there are certain models that we just kind of almost go automatically to. There's the first order stochastic model, and there's the second order model that you can do. So you can do, and those are kind of, those are all over so many fields that it's easy to just go towards that. I would personally start with trying to get you to draw what happens between two time points, what happens between two evaluation points, and then trying to figure out what is the corresponding mathematical model. Because that's what tells me about those level velocity acceleration components that I would need. And I speak often in level velocity acceleration because they have a direct correspondence to 0th first and second derivatives, which means I can get to an exact mathematical model if I can get you talking about points, that is level, velocity, that is straight line change, and acceleration is kind of that quadratic like change. But that's what I would be thinking about. I don't know if that answers that first question. With the second, perhaps tangentially related, but you mentioned lag 2 effects at the beginning. Can you explain how lag 2 effects work when thinking in continuous time? Sure. It's probably simpler to take a back step to 1927 with Ewell. Ewell was interested in, was it Ewell now? I apologize if I'm remembering correctly, but the scientist was interested in modeling sunspots. And so he looked at the connection between the discrete time approximations and sunspots, because he was expecting this oscillatory-like behavior in sunspots. And what he shows is the mathematics of, if you want to have a second order model that oscillates, that actually can correspond to an AR2 model. And so if we start to think about oscillations in between, we can start to think about that in terms of our continuous time, what is happening in between. Now, in order to do this in continuous time, instead of going back 2 lags, what I would do is build that oscillator-like model, which requires actually the second derivative. So you would have not only a latent first derivative, but you would have to have a latent second derivative. And if you incorporate that latent second derivative, you can actually, between 2 time points, you can always integrate a model between 2 time points, figure out those paths for an oscillating-like change between 2 times. Ken, I see you've got a hand up.
Yes, very nice talk. I enjoyed hearing your discussion, the continuous time in relation to the discrete. So thank you. Yeah, so you focused a lot on cross-lagged panel models, a little bit on different scores. So to try to tie our talks together a little bit, suppose you did testing and you actually found that there was a much better fit if maybe you had a growth curve type model, combined with autoregressive, or just a straight quadratic growth curve. So in terms of the fit of the model for the data you have in hand, when you're treating it as discrete, you made the point that there'd be there's multiple models that could have the same fit. How would you interpret that? Like a growth curve model, would you still be able to go to the continuous time interpretation, or combined with autoregressive? Yeah.
So I have done this, Ken. If you go back to those, if you imagine that blue and red that I was doing where I had the time invariant and time varying, if I have enough data points, and I do need like a minimum of 4, I think 4 to be identified, in that time invariant part, I can replace that with a growth curve. And so I can have a random intercept and a random slope, and then still do the state part on top. What I know from the 2 models that I showed today with the cross-like panel model and the exact discrete, because of the equivalence in the red part on top on the state part, it means that I can actually fit a model with the exact discrete model with the growth part, so that you would have growth and variation around that growth that would produce the exact same model fit as the cross-like panel equivalent.
But how would you handle the fact that, say it's a linear growth, right? We know that can't go on forever. So how would you take that into account, right? If you just sort of run out the growth curve, anything we study is not always going to keep going up if it's a positive slope. And
how do you take that into account with the models that you're showing?
I would just describe it as this is hopefully an accurate description for this period of time we're looking at. I wouldn't extrapolate, beyond that.
And the same would be true for the continuous time models. You wouldn't want to extrapolate beyond your data.
Okay, thank you.
My purpose in putting them together and highlighting that they have the exact same fit is basically admitting that you can mathematically do a transformation on many of the models that we fit into a continuous time equivalent, and the parameters change and your inferences change and your understanding of the data change, but fundamentally it fits the data exactly the same. And so this choice between do we do it in discrete time or continuous time is really a researcher choice. And I think we need to think about that like any choice we make with our variables. I know that there's a temptation again to see time as just some kind of index like participant number, but I think we really need to become active in our choice as to how we think about the modeling and how time is incorporated into our models.
But there's the other part, which again, tied between our talks. How do you choose which of those models, right? That you're
well, that's the thing. They fit exactly the same.
Yeah.
So at least in terms of comparing against data, we actually can't. That is not the way to make a choice between them. I mean,
not between the continuous and discrete, but the actual basis of your model. Which model you're going to assume. I mean, did you compare? You didn't compare to a growth curve, for example, model.
I mean, not in what
that was actually better.
Not in what I've shown, no. But you could do those same comparisons. I mean, anything that is doable in discrete time, you can do. Because it's a mathematical transformation, you can do it in continuous time.
Right.
And it just gives you a different insight on the parameters. That doesn't make it any more right or wrong, because the right or wrong, whether the data should be treated as discrete or continuous, is a choice that I'm not sure we can inform directly from data.
Sure.
And so this is one of the roadblocks I run into when I think about going from data to causes. Like, how do we pick between 2 models, discrete and continuous, that fit the data exactly the same?
Well, I think you illustrated it with your examples, that there are some where it makes sense, to view it as continuous, and others where it makes sense to view it as discrete. So
I think that's a wonderful discussion, and I would love to join in with several points. But looking at the time,